All right. For this video, the problem we have is a negative 2x plus 4. So this is probably the most challenging example we've done so far. It has a couple of things to really point out. In the first one, we have the repeated root, which is like this one here. So we're going to utilize that first example again. Um, our degree of the numerator is less than the degree of the denominator, so we don't have anything from the last example. But we also have a new factor here, which is an irreducible uh, quadratic over the real numbers. In other words, x squared plus 1 doesn't have a real valued solution for x. And so how do you handle partial fractions when you have uh, either a combination like this, where you have a repeated root and an irreducible quadratic, or the new part is also how you just handle an irreducible quadratic. So we're going to tackle both of those situations for this particular problem, okay? All right. So the good news is we don't have to do any factoring or anything like that. We can just begin immediately. So we're going to use partial fractions. We have 2x, negative 2x plus 4 over x squared plus 1, and then over x minus 1 squared. Okay. So handling this first one, we're going to have an a term, but since we want the relationship between the numerator and the denominator to be at most 1 degree apart, I need to add more to this. And so this is a quadratic. So I need a linear factor up top. I just don't know what the coefficients are going to be. So I'm going to have an ax plus b for the constant term. And then I'm going to have this is x squared plus 1 is the denominator. So when you have an irreducible uh, quadratic in the denominator, the undetermined partial fraction piece that you're going to get is a combination of a linear term and a constant term. Okay, so it's always going to look like this whenever you have something like this that's irreducible. So this would have been like x squared plus 2x plus 2, which also doesn't factor. Well, yeah, that's a bad example to make up off the top of my head. But if you had a trinomial that didn't factor either, then you would also have a very similar form of this. So whatever the quadratic term is, you're going to have a linear factor on top. Okay, plus, so remember in the first example, we had a repeated root like this. And so I have a c over x minus 1. So I have the linear case, and I have as many of these terms as I do the degree of this. Okay, so this is a 2. So I'm going to have a d and an x minus 1 squared. These terms are constant because the linear factor is constant. If this had been a repeated uh, combination, if we wanted to get really hard, what if you had an irreducible quadratic in the denominator that was repeated root? So something like uh, x squared plus 1 squared. What would that look like? Well, you'd have a linear factor like this, and then you would have another linear factor, but you'd also have this on top as well. So it just repeats. So it'd be a cx plus d over x plus 1 quantity squared, and then a factor like this. So I hope that makes sense, but that's how you'd handle something like this, which would be like, ouch, if you got that. There may be other methods that you could utilize instead of doing perfect fractions in that one. Okay. Anyways, we're going to multiply everything through by this product here. And so we get negative 2x minus 4, not minus 4, plus 4, sorry, is equal to, so ax plus b is going to get multiplied by uh, x minus 1 quantity squared. So we're going to get ax plus b, and we're going to multiply that by x minus 1 quantity squared, since none of those factors factor out or cancel out with the x right here. Okay, and then we're going to get c. So this only has one of those, so it's going to have an x minus 1, the x minus 1, I don't know what I was writing there, an x minus 1, since one of them only cancels with the x squared, and then I have a x squared plus 1, and then plus d. Well, the x minus 1 squared is going to cancel out, but I do have an x squared plus 1 left over there. Okay, so I have some algebra to do to kind of get things together. And the other thing about this example that I really like is this is going to show you another way of finding the coefficients here. Since in the previous two examples, we had linear factors, we could just plug in values for x. In this case, we're going to do something called undetermined coefficients, which will allow us to create a system of equations based on the degrees of the various polynomials. Okay, all right. So first thing, I need to multiply this out. So I get uh, x squared minus, this is a perfect square, so it'll be minus 2x plus 1. Okay, and then I have to multiply that by ax plus b. Okay, so multiplying here, I'm going to get an ax cubed minus 2ax squared plus an ax, okay, plus a bx squared minus a 2bx plus the constant term of b. Okay, so that's going to be this term. Then I'm going to multiply this one out. Okay, so I'm going to get over here, I'm going to get an x cubed. I'm going to get a cx cubed. And then I'm going to get a plus c from the c times the 1 here. And that's going to have a, I forgot the x term there, so it's cx. There we go. Okay. And then I'm going to have a negative c, so I'm going to have a minus cx squared. So c times negative 1 times x squared. And then I'm going to have a minus c times minus c. Okay, 4 terms. X cubed, check. X, check. Negative x squared, check. And a minus 1, check. And that'll get multiplied by c. Okay, so that takes care of that one. And this one's already multiplied out. So this is just a dx squared plus d. Okay. So now I'm going to rearrange these based on undetermined, based on degrees or i's of x. If that doesn't make sense, you'll see in just a sec. Okay, so I have an x cubed. So all of the terms with an x cubed, I'm going to put together here. So I have an a coming from here. I have a c coming from there. So plus c. And then I don't think I have any other terms with that. Okay, and so on the left-hand side of the equation, over here, I have a negative 2x plus 4. So there's no x cubes over there. So these guys are going to equal 0. Okay. All right, let's look at the x squareds. What do we have there? Okay, so I have a minus 2a coming from here. And then I have a plus b coming from there. And so that's nothing else there. And then I have a minus c coming from here. And then a plus d coming from there. Okay. And again, there is no x squareds on the left-hand side, so that's going to equal 0. Okay. And then I have an x term. So I have an a there, and a minus 2b there, and then a plus c there. And that's it. And that's going to equal 0. Okay, and then last but not least, the constant term. Okay, so the constant term, I have well, that's not going to equal 0. Sorry, for the x term, I do have negative 2 on the left-hand side. So this actually isn't equal to 0. It's a minus 2. Sorry about that. I didn't resolve the next term already. Okay. All right, for the constant term, I have a b. And then a minus c. And then I have a plus d. Okay, and that's going to equal a 4, like a 0. D equals 4. Okay. All right. So now I can write this as, you can solve this a variety of ways. It's kind of set up for maybe substitution where you can let A equal opposite of C, and you can get a relationship here. I personally like to write this out as a matrix. So if you can imagine, I have a 1, a 0, a 1, and a 0. And then I have a negative 2. No, sorry, I have a 1. Oh, negative 2. Oh, look, I got confused. I'm looking at this one. Negative 2, 1, negative 1, 1. And this is a 0. That's a 0. Okay. My third one is going to be a positive 1, a minus 2, a 1, and a 0. And that's going to equal negative 2. Then I have a 0, 1, a negative 1, and a 1, and that's going to equal a 4. Okay. So this is my augmented matrix, where this row represents the x cubes. This is the x squared, this is the x's, and this is the constant terms. And then if you can imagine, this is the a's, the b's, the c's, and the d's. Okay, so if you're wondering, like, what is this or how is this set up? That's what I'm doing. So this is a -2, -1. Okay. All right, so I'm going to use technology to solve that. All right. So, like I said, I was going to use technology to solve this. So I made the matrix A, which you can see here is 1, 0, 1, 0, -2, 1, -1, 1, 1, -2, 1, 0, and we have 0, 1, -1, 1. So these are all of the coefficients. This is the x cubed row, this is the x squared row, this is the x row, and this is the constant row. And each of these columns represents the unknown A, B, C, and D. Okay. Then I set that equal to, so I'd had to define another uh, vector, which was our constants from the left-hand side. And so we had 0x cubed, we had 0x squared, we had -2x, and we had a +4 constant. Okay, so I'm going to put those two together, which creates an augmented matrix, which is this one. And then I do row reduction on it, which means solving for it. And here you can see I get D is equal to 1. I get C plus D is equal to -1, but D is equal to a +1. This is really, C gives me -2 here. And then this already is solved for, so B is equal to a +1. And this says that A is equal to the opposite of C, since the sum of these two has to equal this 0. And since we found C was equal to -2, that means A is equal to a +2. Okay. All right, so let's go ahead and jump back to the paper there and write this out, and then we'll finish up the integral. So this is just summarizing what I said from the technology. So we have found D is equal to 1, C is equal to -2, B is 1, and C and A is opposite of C, which is +2. Okay. All right, going back up here, then for our terms, okay, I'm going to be plugging those in. So I want to integrate A is 2x plus B was 1 over x squared plus 1. Sorry, I can't see that. So this is A and B over x squared plus 1. Okay, and then plus C was equal to a -2. So it's going to be -2 over x minus 1. Okay, and then plus, and D was equal to +1. And that's going to be over that term there. So it's going to be over 1 over x minus 1 quantity squared. Okay. All right. So we have a couple integrals to do still. Note that this integral here is going to require two different things. I'm going to split this integral, 2x over x squared plus 1, and that'll become a u sub, and then plus 1 over x squared plus 1. So that integral is actually going to be a trig sub, which we learned about earlier. Okay. All right. And this integral here is going to be a simple u sub with a natural log. And this integral here is going to be a same u sub. However, this is going to be a power rule since this is a -2 exponent, which I can add 1 and divide by. Okay. So these two integrals will be pretty easy. The first of these two integrals will be pretty easy. The second one will be a little bit more challenging because of the trig sub. But let's go ahead and knock out the easy ones first, and then we'll tackle the harder one. All right, so what I was saying is 2x over x squared plus 1 plus 1 over x squared plus 1. So that's the splitting up I was referring to, minus 2 over x minus 1 plus 1 over x plus 1. No, sorry, x minus 1 quantity squared. Okay, so those are the terms. We're going to do this one and then these two, and then we'll come back and tackle that one. Okay. So for this one, I'm going to let u equal x squared plus 1 for this one here. That gives me that du is equal to 2x dx. So you can see right there, that's going to be the part of the numerator, and then the dx is going to be right there. So actually, that's all taken care of by the du piece. Okay. So this integral is going to be du over u. And this is going to equal the natural log of u. I'm foregoing the absolute values because the u is x squared plus 1, which is always positive. Okay. And then, so substituting that back in, you get that this is the natural log of x squared plus 1. Okay. So that's the result of this integral. Okay. I'm going to look at this integral next. So both of these integrals are going to use the same u sub. So this is for both. This is going to be u equals x minus 1, and du is equal to dx. The resulting integrals will be different, but the sub will be the same for both. Okay. So for this integral, let's take care of that over here. I have a negative 2, the integral of du over u, which is going to give me negative 2 the natural log absolute value of u. And subbing that back in, I can natural log of x minus 1. Okay. So that's that integral. And this integral, I have the integral of u to the negative 2 du, where I've plugged in that this is my u, and then integrating that, I get negative 1 u to the negative 1, which gives me negative 1 over x minus 1 as the result of this integral. Okay, so I have this bit right here, I have this bit, and I have this bit. Okay, so now I need to worry about integrating this one. All right, so we have the integral of dx over 1 plus x squared. This is a plus x squared, and so that form makes me believe that the positive form of this substitution should be so just like before, starting with cosine theta squared theta plus sine squared theta equal to 1. And looking at this has the same form, but plugging that in is not going to work because I don't have the mix of variables. So I'm going to divide everything through by cosine squared theta. Okay, and that's going to give me 1 plus, and that's going to be, so this gives me 1 plus tangent squared theta is equal to secant squared theta. So that looks really promising because 1 plus tangent squared is exactly what I have here. So it looks like I need to let x equal tangent theta. Okay. All right. So if I do that, then dx, that's an x, is equal to secant squared theta, d theta. Okay. So dx is this, d, and then plugging everything in, you get the integral of dx is secant squared theta d theta over 1 plus tangent squared theta. Okay. But if you look here, 1 plus tangent squared theta is secant squared theta. So this actually reduces to just the integral of d theta, which means that this is the integral of theta. So it actually collapses pretty quickly. And then looking back at our u sub, that means that solving for theta here, that in terms of x, this is equal to arc tangent of x. Okay. So with all of these pieces, finally putting it together, our final result for our integral is a lovely little bit. Let me see if I can find some room up here. Putting all the pieces together, then this integral is simply equal to the natural log of x squared plus 1 plus what we just found, the arctangent of x minus 2 times the natural log absolute value of x minus 1 minus 1 over x minus 1 plus a constant. Okay. All right. So that problem was a little bit more involved. Like I said, part of the challenge came from the fact that we had an irreducible quadratic, which kind of resulted in finding two additional constants. And then we also had the repeated root. So we had to take into account the fact that we had multiplicity of degree 2 in that regard. Okay. All right. I hope this video was helpful, and I'll see you in the next one.